Okay, so today Shashank will tell us a lot about codes and
Okay, so we're talking about explicit codes approaching generalized Singleton bounds. We'll start with the basics of codes, etc. The first hour will mostly focus on setting up the right context, etc. Code C is a subset of sigma to the n, where sigma is a finite alphabet. And n here is called the block length of the code. So code C can be seen as a collection or a set of strings of a common length n. The two most important parameters of a code are its rate, which is a measure of how large this set is, relative to the block length n. And the other parameter that is of relevance is the distance delta. So we look at any two distinct strings in the code and we look at their Hamming distance. Ideally, I should normalize it, but I think I'm going to use this delta notation a lot. So I'm just going to call this as the normalized Hamming distance already. So both rate and distance are going to be numbers between 0 and 1. And generally, we consider a family of codes, and we say a family of codes where n goes to infinity as so an infinite family of codes has rate r if for everything in the family there is a uniform lower bound of r. Okay. So why are these two important parameters, rate and distance? Well, the typical use for codes has been for error correction. And let's see how these two parameters come in while doing error correction. So let's say I want to communicate a k-length string x over the alphabet sigma. Then the way we use these codes is to first decide a bijection between sigma to the k and the code C. And for this to happen, it must be the case that k is equal to Rn, where R is the parameter that we defined there. So this x is mapped via this map to a vibe which belongs to C. And C, remember, was subset of sigma to the n. So if this bijection is happening, then it must be also the case that k is less than equal to, that n is larger. And then when this code word is passed through noise, then it may get corrupted to some y tilde, which is somewhat close to y, but different from the y that we intended. The code is supposed to be designed in a way that we can just look at y tilde and recover what y was. This part is called decoding. And once we have y, we can always invert this map and get x as well. But the whole point is that even if there was some noise in between, this code facilitates recovery of y. And to just draw some picture, let's say this is sigma to the n. The code is going to look like a subset of the sigma to the n space. Let's say this is the y that we are looking at. Then as long as the noise was not too much, let's say this was y tilde, then and in particular, y tilde lived in this Hamming ball of delta over 2 radius. Then we can at least theoretically try to map y tilde back to y. Simply by, so what would be the decoding mechanism? So we look at y tilde here and assign y to be the nearest code word to y tilde. Or mathematically argmin of the distance between y. Just write that. Okay, so this kind of intuitively makes clear why distance might be relevant to error correction, because the larger that these code words are separated, the more errors we can hope to correct. Okay. And we also want the distance to be as large as possible. Likewise, the rate here is a measure of how much redundancy we are adding, how dense the set of code words is. And again, we want the rate to be as large as possible. So both of these, as we said before, are numbers between 0 and 1, and we would like them both to be as large as possible. So there are two challenges here relevant to error correction. One, the combinatorial challenge is to design these codes with as much distance as possible between code words. And there's also an algorithmic challenge that, this we also typically want to do efficiently. Find the nearest code word, because the trivial algorithm is to try everything, which could take too much time. Okay. So let's talk about this combinatorial challenge. So the first question that arises is, we have two parameters, delta and r. What delta r values are allowed together? Ideally, we would have both to be 1. And that's not possible. So let's see why. There is some trade-off, like tension between these two parameters, the distance and rate, because as we increase the rate, this set becomes denser and denser, and then it becomes impossible to maintain the well-separatedness property. So the most intuitive, most basic trade-off of this form is called a Singleton bound. It says that the sum of these two parameters cannot be cannot be more than 1.
Okay. Sorry, you've normalized your Hamming distance.
Yes.
error.
So Hamming distances are always normalized. Okay. And let's see a very quick proof of this. Let me fix some Rn minus 1 many coordinates out of n. So the total is n. How many assignments can I give to this Rn minus 1 many coordinates? Would be sigma to the Rn minus 1. And the total number of code words is sigma to the Rn. So by pigeonhole, there are two code words that have the same first assignment. So these are two distinct code words, say F1 and F2, that agree in this portion. Now this already means that they only disagree in the remaining part. So the best distance we can hope for is only 1 minus r. So the distance in this case would become So yeah, in singleton bound, there's also this plus 1 over n, but typically because we consider infinite families, this 1 over n term just goes away. So anytime we have a rate R code, the best distance we can hope for is 1 minus R. So the next question that arises is, are there codes that actually get there? This is an impossibility result, and also gives us a standard to check our code parameters against. And when Yotam gave his talk, I think he had 3 type of constructions for expanders. I think it's the same 3 categories for codes as well. So there are random constructions. There are algebraic constructions. Then there are combinatorial or linear algebraic constructions. With random constructions. So suppose sigma was actually a finite field of size q. There are other random constructions also. For now, let's focus on this. Then a random subspace of dimension Rn has rate R pretty much by definition, because the size of this random subspace is q to the Rn. So it has rate R. The question is, how does it do on the distance front? And the distance, so this already means that rate is R. Can be shown that distance can be made larger than 1 minus R minus epsilon for all epsilon. So the right way to quantify this is that for all epsilon, there exists a Q such that a random subspace of dimension Rn will have distance more than 1 minus R minus epsilon with high probability.
There's also some quantification over n for large enough.
So the high probability will involve n, but for large enough n, yes. So random subspaces do well, random sets also do well. There are multiple such constructions. If you know of the GV bound, this is also a special case of the GV bound in the limit of large alphabets. But okay, so this already means that one, constructing explicit codes with this kind of parameters is a de-randomization challenge. It's also a de-randomization tool because once you construct them, you can use them in places where randomness might be used. And for this kind of random subspaces, we do not expect efficient algorithms in the sense that we wanted for decoding, because they just lack enough structure. So like towards the goal of de-randomization and hopefully getting algorithms, let's look at more explicit constructions. And the second category that we had there was algebraic. So let's look at probably the most well-studied family of codes called So Reed-Solomon codes are based on bounded degree polynomials over finite fields. Okay. So every code word is associated to a degree Rn polynomial. Okay. So if we have to choose a degree less than Rn polynomial, it's sufficient to choose Rn many coefficients for this polynomial. Let me name this Rn parameter as k. So this corresponds to the polynomial So we choose k coefficients, and for those choice of coefficients, we construct this polynomial of degree at most k minus 1. And the code word looks like this polynomial evaluated at n distinct points. So this is f of alpha 1, f of alpha 2, and so on. So each code word is associated to a bounded degree polynomial. And the code word actually is computed by evaluating this polynomial at n distinct points. The rate, again, the number of polynomials that we have is q to the k, which again, by definition, we have chosen it to have rate r. Again, the question is, what is the distance of this? And for any two degree k polynomials, they cannot have more than, they cannot agree in more than n minus k places. So let's say there was another polynomial. It would also be evaluated on the same points. Well, if they agree in a lot of places, then we can look at the difference polynomial f minus g, and it will have a lot of roots. Because everywhere where f and g agree, f minus g has a root. F minus g is still a degree k minus 1 polynomial. So the total number of agreements can be at most k minus 1, which means that they disagree in at least n minus k plus 1 positions. Which, yeah, if we substitute k to be Rn and compute the Hamming distance, this will exactly be the Singleton bound parameter. So the distance between F and G. Great. So we had the Singleton bound and these Reed-Solomon codes achieve it exactly, which is perfect. For random constructions, etc., we still had to deal with the epsilon slack. Here it is exact. That's why they are used pretty much everywhere, like even for small values of Q. They're widely deployed in practice and stuff. Okay, so these are explicit also. So they also come with algorithms. So delta was the distance, which is 1 minus r. They can be decoded from half the distance in near linear time. So as for the error correction task, these are really good for that. Couple of drawbacks that they have is we needed n distinct points. So this entire argument that we had with number of roots, that only works when these points are distinct. So we need this field to have at least n distinct points, which means that Q has to be at least n. And the second drawback is, well, half 1 minus r is good, but it's always still at most 50% of the positions or 50% errors. What if we have more than that errors? Can we still do something or is all hope lost? So again, if we go back to that picture, previously we said, okay, if the number of errors was less than delta over 2, then we could hope to do things. What about if the error exceeds delta over 2? And let's try to address both of these separately. So what happens for the case of smaller alphabets? We'll not be talking too much about smaller alphabets, but let's just address them once. Well, first, for any code of alphabet Q, think of Q as, for example, 2. So we are looking at binary alphabet. If if we are targeting a distance of more than 1 minus 1 over Q, then the rate must be 0. This is called the Plotkin bound. So for example, for Q equals 2, this means that it is hopeless to construct codes with distance more than half, at least with positive rate. This is in contrast with the large alphabet case where we saw that we could always choose R to be small and get very large distance codes. Okay. But if we wanted to construct, well, also in particular, like here we had R versus 1 minus R minus epsilon, right? So if we chose, for example, R to be epsilon, then we could get codes that had a trade-off of epsilon versus 1 minus epsilon kind of trade-offs. So if we are just targeting this, one could hope that maybe we can't do it with Q equals 2. Q has to be omega of 1 over epsilon, but it doesn't have to grow with it. Could be a large constant, depending on the slack. Secondly, for delta less than this threshold, between 0 and 1 minus 1 over Q, there are codes with rate that is 1 minus the query entropy of delta. It's not super important what this query entropy function is, but it is always positive. This is the Gilbert-Wasserman bound or GV bound. But this is again based on the probabilistic method. Like I said before, the random argument here is a special case of this GV bound. What about explicit constructions? So for this entire range, the same range 0 to 1 minus 1 over Q, there we do know of explicit codes with positive rate. This positive rate might not be as good as the one promised by probabilistic method, but hopefully someday. Okay. But for the kind of trade-offs we are looking at, let's say R versus 1 minus R minus epsilon, this says that Q has to be a large constant. And what does this explicit construction look like? The idea is something called concatenation codes. So we constructed codes that are over large alphabet, are very optimal, but only over large alphabet. So can we use them to construct codes over smaller alphabet? That's the idea, and somewhat natural that here's how we proceed. That let's say X was the message. We encoded it, let's say with Reed Solomon. So we get n different chunks here, each one of them an evaluation of the polynomial. So this is a symbol in FQ. This is another symbol in FQ. The key idea is that we take an inner code and encode this block further. And this inner code is over a smaller alphabet sigma n. Same thing we do with the second one, and so on. and then put all of them together into a single string. Well, at least alphabet-wise, because we are encoding this inner code, which is of alphabet sigma n, the final code also has, this is a string over sigma n. What we do require is that this encoding is only possible if the size of this inner code is equal to the alphabet of the outer code. Only then we can do this bijection here. The nice thing is that this inner code can be shared among all these encodings. So we just need to find it once and then reuse it. And if we are thinking of an infinite family, this could be found by brute force search, for example. We do know that probabilistically they exist. Let's say this Q was constant, then this could definitely be found by brute force search. But even if the alphabet is growing mildly, such as N, such a code can be found and then reused. So this was the first explicit construction of binary codes, for example, with constant rate and constant distance. Okay, yeah, I need to tell you about the parameters of the final code. So yeah, it's not very difficult to show that the rate of the final code, let me call it C concat, is actually the product of the rates of outer and inner code. And same with the distance. And also recall that the final codes, the concatenated codes alphabet is inherited from the inner code. So we should really judge it according to the trade-off of the inner code. So delta n is here, R of Cn is here. Let's say we had the best possible trade-off for the inner code. That could be possible. There are these additional multiplicative factors that we get. Let's say we picked R to be, like RC out to be very large. Let's say this was some 1 minus eta. Then by singleton bound, unfortunately, delta C out will have to be only eta. And then we get a much lower distance. So like the best trade-off we could have hoped for was delta seen and R seen, but what we are getting is something close to R seen, but the distance is much lower by an eta factor. So is all hope lost? We'll come back to this. Like there are ways to remedy this. And also, like I must remark that here, this also illustrates why it would be nice to have Reed-Solomon-like or parameters near singleton bound, but with constant alphabet, maybe dependent on epsilon, because then this inner code would truly be constant size instead of finding it every time with some poly and runtime. So this was about smaller alphabet. Let's also discuss something about this error correction radius being at most 50%. First of all, if two code words, let's say F1, F2 are separated by delta, then hoping to correct more than delta over two errors is in some sense hopeless, because we can look at the corruption such that there is a string sitting exactly between them. And then which one do we answer? We are only supposed to look at the corrupted thing. But the hope is that maybe we could output both of them, as long as they're not exponentially many such code words. So this is called list decoding. It's a wishful thinking that we can look at such a corrupted code word and try to output the entire list. Of course, the list might be too large, and then this is hopeless. But in some sense, this is always a reasonable thing to do, because there is always a threshold which is a function of the distance. And this threshold is strictly between delta over 2 and delta. Such that so if we look at the set of all code words that are close to a particular fixed f tilde, how close? J of delta close. Then the number of such code words is only polynomially many in n. We're saying that this is f tilde. We saw before that because of the distance of a code, up to delta over 2, there is only one possible candidate. But even if we were to extend it beyond delta over 2, up to some threshold, then maybe there's not just one. This was F1. There might be multiple, but not exponentially many. So one could hope to output them. And the main punchline is that this J of delta, let's say if delta was 1 minus R, then J of delta is 1 minus square root R. It's a simple exercise to see that this is actually between 1 minus R over 2 and 1 minus R. So by making R approach 0, this correction radius can actually be made as close to 1 as possible. So we can take these balls radius to be as close to 1 as we want. You just have to correspondingly pay in the rate. Of course, this is just a combinatorial bound. There's a whole different question with algorithms. So this set, I'm going to call this, let me define it again. So this is called the list of code words around any f tilde, and let's say any arbitrary radius beta. This is the set of all code words such that they are close to the f tilde. And what this is saying is that this set is of small size relative to the entire code. Um, Just to illustrate this point, if this is R, then this is the 1 minus R line. And the unique decoding radius that we had of delta over 2 would look like this. The Johnson bound looks like this. So in the case when R is very small, it approaches an error correction radius of 1. So up to here, we know that the list is of bounded size. Here we know that this list is of size 1. In the shaded area, it is of small size. And for the special case of Reed-Solomon code, in the late 90s, Guruswami and Sudan gave this algorithm. That could correct 1 minus square root R errors. And the fact that we can correct almost close to 100% errors, like 99% errors, etc., that has had a lot of applications in complexity theory, etc. This is actually the kind of regime that we care about when the number of errors are too large. This is based on polynomial interpolation. Maybe I'll not go into the details. So the idea is that we look at this corrupted f tilde, learn a bivariate polynomial out of it via interpolation, and then all the list code words exist as roots of this bivariate polynomial. And all of those steps are algorithmic. We just need to solve some linear systems, etc. Okay. But there's also this gap between 1 minus square root R and 1 minus R. So the singleton bound argument can be modified to show that even for list decoding radius for rate R code, we cannot do better than 1 minus R. So 1 minus R is the best error correction radius also we can hope for. But this gap between 1 minus square root R and 1 minus R is not so clear. And for a while, people tried to push this 1 minus square root R to 1 minus R until so Parvarish Vadi and Guruswami Rudra, there were a bunch of results that together showed that something called folded Reed-Solomon codes So if we look at a rate R code from this family of folded Reed-Solomon codes, I'll come back to what these folded Reed-Solomon codes are. When you look at a rate R code, it can be list decoded up to 1 minus R minus epsilon. So this gap between 1 minus square root R and 1 minus R does not exist for these codes. And so, yeah, in this language, what this means is that the list is bounded by a polynomial. In fact, this list for any f tilde is of size n to the order 1 over epsilon. So any code which is of rate Rn can be list decoded up to this is said to be achieving the list decoding capacity. Because this 1 minus R is the best we can do, it's called the list decoding capacity. And codes that actually can have small lists up to that are codes achieving list decoding capacity.
Dependence on epsilon is also, sorry, is also correct.
Yeah, so initially this was the result, but we'll see what the correct thing to expect is. Yeah, so exactly like this list size dependence, what is the best we can do? And again, maybe it's best to start with what we should expect. Let's look back at the singleton bound argument, right? Because that said that beyond delta over 2, we must have 2 code words. Let's look at an analog of the singleton bound for list decoding. This is called generalized singleton bound. So remember, we said that look at a rate R code, maybe Rn minus 1 first coordinates. And there are a bunch of code words that must agree in this position by pigeonhole. And we did this argument using 2 F and G. Well, there are actually Q many of them. And even more if we just reduce this Rn minus 1 to Rn minus. Let's look at 3 of them. Then what's the best G we can construct when we are trying to refute these 3 code words together? Let's take G to be, by G, I mean, okay. Let's say F tilde. So in the first R fraction, F just copies this common value. In the remaining 1 minus R fraction, it copies first 1/3 of the first guy, second 1/3 of the second guy, and third 1/3 of the third guy. So what do we get? That the distance of F tilde from any of these is actually 2 over 3 1 minus R. Right? Because 1 minus R, here it simply copied the values, so there's no distance here. In the remaining 1 minus R, it agrees on 1/3 of the time. The remaining 2/3 it may disagree. Might be better than that, but so what we get is for any time when the decoding radius is more than 2/3 1 minus r, the list must be of size at least 3. Or the contrapositive, if the list is of size 2, then the decoding radius must be at most 2/3 1 minus r. And of course, we can extend this argument to say if beta is s minus 1 s, that is 1 minus r. Then the list must be of size at least s. So this means that if we are to approach 1 minus r, then the list must be of size roughly 1/epsilon at least. Because to approach 1 minus r, we have to take s to be of the order of 1/epsilon. So here the best we can hope for is omega 1/epsilon. And it turns out that the random constructions certainly achieve this omega 1/epsilon. They go off 1/epsilon. And this gap was known already, and there's been a lot of work trying to address this. So like I mentioned, this folded Reed-Solomon codes, the initial list size was n to the 1/epsilon. Guruswami in 2011 showed that the list is actually contained in in 1/epsilon dimensional affine subspace. So this does not directly lead to an improvement in the list size, but it gives more structure to it. Because Q is of the order of n, the number of affine combinations we can take is n to the 1/epsilon, or Q to the 1/epsilon. But he proposed this constant dimensional affine subspace as a way to improve list sizes, and that indeed happened by Weir and Lovett in 2012, who constructed these objects called subspace evasive sets. So the idea is that these are constant dimensional affine subspaces. We can pre-encode the code, take a further subset so that all constant dimensional affine subspaces have small intersection with this pre-encoding. So this allowed the new list size to come down to 1/epsilon to the 1/epsilon. Which is nice because at least it's a constant, not depending on n. Then there were other works also trying to use other variants of codes. But in Koparty, Ronzavi, Saraf, and Wooters showed that folded Reed-Solomon codes themselves, just using the fact that the list is contained in these constant dimensional affine subspaces. Well, we don't need to do this pre-encoding. Hamming balls and affine subspaces don't go well together directly. At the end of the day, this list is coming from a Hamming ball. So a Hamming ball and affine subspace is not going to intersect a lot. We don't have to take the worst case form. And they were able to get, again, a list size which was close to 1 over epsilon to the 1 over epsilon. And this was also, this was 18 journal version later. A lot of this proof method, etc., was simplified and bound slightly strengthened by Tamo. Then this was improved to 1 over epsilon square in one of my results. And then finally, recently, a few months ago, Chen and Zhang were able to get the perfect 1 over epsilon result. So all of these rely on the fact that list is contained in the 1 over epsilon dimensional affine subspace, which is an argument coming from polynomial interpolation, etc. Okay. So this is the optimal list size and we can get it. The main result from this talk is an alternate construction with a similar list size, but a very different kind of construction, which is combinatorial. That also does not have to go via all of this. It directly gives the right result. I think maybe we can take a, okay, maybe I can just do the motivation for why should we look beyond algebra for codes as well. And then we can take a. So these codes are nice, except they still have some limitations. Well, first of all, alphabet size is n to the 1 over epsilon square for FRS. Ideally, we would like to have codes that have large constant size alphabet instead of growing with n, similar to the Reed-Solomon limitation. Secondly, these constructions are all very rigid. The proof methods seem very tailored to the algebraic setting. And there's a lot of other work in coding theory, right? You might want to have the best of both worlds. Maybe have locally testable codes also along with list decodable codes. And these are algebraic codes. It's difficult to imagine how to get these to be locally testable, etc. So we want a more flexible construction that might go well with other code constructions, especially with locality type of properties. Thirdly, like all of these proof methods and the improvements that we have, they are fairly complicated at this point. Proof of small list size. It is. There's this question of linear time algorithms, which some combinatorially constructed codes have. But for Reed-Solomon, etc., even their unique decoder runs only in time near linear, not truly linear. But we do know of codes that run in time truly linear, I mean decoding. So if we had more combinatorial constructions, we would also expect that maybe we can have list decoding up to capacity in linear time. Which, at least if we are going via the algebraic route, even the unique decoder is not truly linear. So that seems a little hopeless. Yeah, and in general, like the algebraic setting, the improvement from Johnson bound to further to capacity, etc., the math works out, but it feels a little mysterious because it's based on interpolation. So our main result is combinatorial construction that approaches the generalized Singleton bound directly with this sort of optimal list size. And it's based on spectral expanders, like a local to global de-randomization using spectral expanders. So if a code approaches generalized Singleton bound, it automatically also gets to list decoding capacity with optimal list sizes. That is only strong. Take a break now.
Come back when? 5
5
minutes.
minutes. Wanted to get to the combinatorial construction. Let me start by reminding you what expander graphs are. We'll only be using bipartite expanders. Bipartite constant degree regular expanders. Let's say the two vertex partitions are A and B. The degree for each vertex is D. And we say this is a lambda expander. If the second largest singular value of the L by R bi-adjacency matrix is at most lambda. And the main thing that we are going to use here is the expander mixing lemma, which is, let's say we have two sets here, S and T. In fact, we'll only be needing an upper bound on this. But We'll only be needing the weaker variant. So the number of edges between S and T can be approximated by D over N, which is the global edge density, multiplied by the total number of possible slots between S and T. So D over N is the global edge density because each vertex has D edges leaving it. The number of slots between S and T are S times T. And for every S and T, this approximation is almost correct, up to this error that has lambda with it. So generally we write the error term as lambda D square root ST. I'll just be needing a weak variant of this where it's lambda dn. Okay. And the key part is that there exist constructions of bipartite lambda expanders for lambda as small as we want. Just have to correspondingly pay the degree. So there exist infinite families of such graphs. We are going to leverage that pseudo-random object, that infinite family, to construct an infinite family of codes based on these graphs. And really, these expander graphs excel at what is called the local to global phenomena, where we put some objects in these local vertex neighborhoods, and then we get to see that property over the entire global graph. The main key point of the construction is a local to global phenomena for the generalized Singleton bound. So even before we go to generalized Singleton bound, let me show you how to use this for Singleton bound, like codes approaching Singleton bound. And this is the famous construction of Allen, Edmonds, and Luby for distance amplification. Be clear in some time. So let's say we have a graph that is n vertices on both sides and D regular. Then we take a C out. This is an outer code of block length n. And alphabet, let's say sigma. So a code word of this can be associated to the vertices here by mapping them coordinate to vertex. And let's say there is an inner code. The inner code has alphabet sigma in, and the block length is D, the degree of the graph. And we have this condition that number of code words in Cm equals the alphabet size of sigma of the outer code. So then when we map this coordinate to vertex, then each symbol here can be further encoded using the inner code. And that will give us D symbols of sigma n. We can place these D symbols on the edges here. So it's really concatenation, but happening on a graph. Okay. All we need to ensure is that the block length of the inner code matches the degree of the graph. And previously I pointed out that for concatenation, we have this loss that happens due to multiplication of the outer code. So just to rewrite that, now the code lives on edges. the concatenated code lives on the edge space, and the rate and distance are both products of the outer code and inner code. And suppose we choose this RC out to be some very large number, so that the rate is almost same as the inner code. This delta C out is going to bite us because this 1 minus eta means that the delta C out can be at most eta. So what this AEL construction does is it does one more level of processing using the graph now, that we look at the right vertices. There are a bunch of edges incident on it. And we call all of the sigma in symbols that we see on a particular right vertex as a single large symbol. So if I call the final AEL code as CAEL, then sigma CAEL is sigma into the D. So this operation of bunching together multiple symbols into a single one is called folding. This is precisely what was going on with folded Reed-Solomon codes.
Shashank, so
Yeah.
can you say what is the resulting block length of the
Right. So the final code lives on the right vertices, and so the block length is just n. It's the size of the right partition. Yes. Right. So the final code looks like n different coordinates. The coordinate number 1 will just group together all the sigma, d many sigma in symbols that it sees on its edges. So it's a pseudo-random way of scrambling these symbols. And so this folding operation does not really change the rate of the code. So the rate here remains same. But as you can imagine, the distance might increase when doing this folding, because if we have two strings that differed in some places, now they only need to differ in one of these right incident edges for that right vertex to be counted as a difference. It's a direct product kind of thing. So the distance does increase, and it goes from so it goes from being a product to this decoupled expression between delta C in and delta C out. So even if delta C out were to be very small, let's say eta, then I can correspondingly make lambda to be even smaller and be as close to delta C in as I want. Of course, the cost for making this lambda small goes into D, and that D shows up as the alphabet size here. Okay. So the way this AEL amplification is typically used is we choose the Cin to be either a Reed-Solomon code or a random linear code with near singleton bound like parameters. So it already has R versus, maybe I shouldn't call it R given everything is R, but let's say this was rho, and this could be taken to be 1 minus rho. And then we'll get something that is very close to rho versus 1 minus rho, as long as the outer code has some constant distance and high rate. And the nice property is that the final code inherits a lot of locality properties from Cout. So for example, if Cout was LDPC, that is, the code can be described by using a bunch of local checks. There are many checks, but each check only involves some constantly many coordinates. Then those kind of properties are also inherited by the final code. but now with the parameters of Reed-Solomon code.
Shashank, the way I should think of this is like the Cn is a subset of sigma into the D. So now you've kind of, instead of having like one sort of symbol of Cn, you've like allowed it to be the sigma into the D, which lowers your rate, but the benefit is your distance goes up by quite a bit.
No, the rate will not be lowered.
By a little bit, right? Because
You mean at the folding step?
no, just like the whole thing. You transfer
Oh,
C
okay.
out to something with slightly lower rate.
Right. Yeah, I would think of actually preserving the parameters of Cn and like think of RCn and delta Cn as some fixed normal numbers like 0.3 and 0.7. And then RC out is lowering the rate by a little bit.
By a little bit, yes.
Yes. And for concatenated code, the distance would have been really bad.
Yeah.
But the AEL part is kind of saving the distance again. But yeah, so the RCn and delta Cn, etc., those parameters are for a constant size object, for a degree. So those objects are over block length D. The degree can be taken to be constant for an infinite family. So for those, we could also do brute force search and find the best possible codes. So the Cn was always living in this local neighborhood. And we get an infinite family of codes with the similar parameters as this constant size object.
If you read Solomon codes, right, the outer alphabet's not going to be constant size.
So if you use, you mean as the outer code?
Yeah, it's the outer code.
Yeah, so the
it
outer
says
code,
n, but then
yes.
it's log n, so then you.
There are ways to do that, but generally we could take the outer code, for example, to be a Tanner code based on expanders. So it's a large constant size alphabet.
Right.
And because we can take these outer code, all you want is large rate and constant distance. You can even start from a binary one and increase its alphabet by folding, etc. So alphabet size is not that much of a barrier because we can get away with arbitrary distance. Yeah, so the rate distance trade-off of the outer code does not matter at all. As long as it is high rate.
You also need like some constant distance, just a
Yes,
small
yes.
constant. Yeah.
So yeah, so for example, for rate R, let's say R of C out was 1 minus eta. It would be okay with distance being eta to the 8. Let's see the proof of it. It's really simple. So the rate computation is pretty much already there. Let's focus on the distance. Right, so let's look at the distance of this AEL code. Let's consider two strings, let's say H1 and H2. They would be differing in some delta out fraction. Right? Whenever they differ, because of the inner codes property, some delta n fraction of these neighborhoods also differ. And the hope is that they go all over the place here. So even though here delta out may have been small, because some constant fraction of the neighborhoods differ between between H1 and H2 every time, a lot of right vertices will see this difference. Okay, so let's say S is this set, and T is the set where we see at least one red edge coming in, where H1 and H2 are different. So we'll upper bound and lower bound this EST quantity. For the upper bound, we'll just use expander mixing lemma. I'm going to skip the size of S. For the lower bound, for each of the vertices in S, we know that a constant fraction of edges, in fact, we know exactly how much. So for every vertex in S, this would be delta C in times T. Many edges are where H1 and H2 differ. This is just based on the distance of the input. Okay. So just lower bound T from the right hand side. What is S here again? S is where H1 and H2 differ. These are two distinct code words. So they would be differing in some delta auto fraction of positions. H1, H2 are code words of the outer code. So yeah, just rearranging, we get this lower bound on T over N, which pretty much only depends on delta C in minus an additive lambda base term. Okay. So one simple lower bound and the upper bound from expander mixing lemma. That's it. And really, this is the kind of property we'll use again and again, that every time there is a constant fraction set S for which every neighborhood, a constant fraction of every neighborhood in this set S is colored with, let's say, red color. Then on the other hand side, let's say every time some alpha fraction was being colored. Then on the other side, we can make this set of vertices witnessing the red edges as close to alpha as we want. And this is reasonable because even if this was not a bounded degree expander, if this was a complete graph, then we can get this property just based on one vertex. As soon as we color one vertex as neighborhood, an alpha fraction of that, on the right hand side, we'll get alpha fraction of the right neighborhood. So this computation is just more robust version of that for bounded degree expanders. So yeah, this can be used to, one more thing, the alphabet finally that we used was sigma into the D. If we choose this to be a Reed-Solomon code, the inner code, then this can be made essentially D to the D, which is all okay because it's still constant. So we are getting codes that approach singleton bound, that where the alphabet only depends on epsilon and not on n. There are other ways to get constant size alphabet approaching singleton bound using AG codes, but this is far simpler than that. Okay. So what we'll try to do is do a generalized singleton bound variant of this. Before we go there, let me mention some strengthenings that we will be needing. So like this local to global is also a bit like induction, where it's easier to prove stronger properties. If you assume a stronger property for the local object. So I think when we started, we were looking at this kind of definition. Then we said, okay, this is general list decoding. The generalized singleton bound said, let's say the distance is delta or 1 minus r. So this is the best we can hope for based on the generalized singleton bound. That for k minus 1 over k, we have list size of just k. So we did the proof with k equals, let's say 3, when 2 over 3 delta. The best we can go for is 2. This is equivalent to saying that the max of these distances is always more than k minus 1 over k. So all of them cannot, whenever we take k code words, all of them cannot be in a ball. That's equivalent to list decoding, or the max is larger than this radius. So the strengthening that we are going to use is, this is actually not max, this is for all g, h1, h2, hk. So the next strengthening that we have is again for all g, h1, h2, hk. Instead of max, we use the average. Or I can change this into sum by removing normalization. And the final strengthening that we need is, so this is called average radius list decodability for clear reasons. We are looking at the average distance. So final version that we will need is average radius with erasures. Which is to say now this G, which is an arbitrary string in sigma to the n, won't just be having symbols from sigma, will actually be sigma union a null symbol is used to declare erasures. And again, for all G, for all H1 to Hk, if G has S fraction of these erasure symbols, then their distance is k minus 1 delta minus S minus epsilon. So this erasure is, for Reed-Solomon, you can just imagine that as ignoring some evaluation points. We're not getting anything out of this erasure, but we also know where it is.
You don't count it in the distance.
We don't count it in the distance. So the distance is made up of only non-null symbols. And thankfully, even this most strengthened version, random linear codes, as well as folded Reed-Solomon, both of them satisfy these properties. Okay. For random linear codes, this just involves a simple union bound over all erasure patterns. For folded Reed-Solomon, that just looks like removing certain evaluation points. The proof only uses distinctness, so it doesn't matter. Now with this, I think we are ready to prove the main generalized Singleton bound. Right. So the result can actually be framed as a local to global result for this entire property, but I'm going to prove something slightly weaker because I think it's a little more intuitive to do. So for k equals 2, what does the Singleton bound or general, that's not really generalized Singleton bound, looks like this. K is 2, so this will just become delta minus S. Right? This is just the triangle inequality applied to distance. Because H1 and H2 are delta far, even if we have a G in between, the sum of distances is at least. Let me define this. So this is the set 1, 2 to be so if only first term was here, the indicator of Gi not equal to H1i, this would be exactly the Hamming distance between G and H1. We're taking the product of both these indicators to say that we're counting the number of positions where both of these are errors with respect to G. So these are some common error locations. And if we think again about the triangle inequality, these common error locations are actually counted twice. So I can add the 1, 2 here. And that extra term is going to be very useful for larger K. So we generalize this definition first. Um, with some set P. Or P. Look at the product of all indicators. And what we are really going to prove is the generalized Singleton bound in the form of
What is G sub I?
G sub I is the ith coordinate of G.
Okay.
Yeah, and Hg sub Ji is the ith coordinate of Hj. Um, so the proof will be via induction on K. And this is the kind of inductive claim that we will prove. Of course, this is only a strengthening because that can be at most, at least 0. So let's give something stronger. This is slightly confusing because all the erasure stuff, we will only be using it in the inner code. We'll not worry about it in the global code. And I'll remark exactly where the erasures come in. So this is the inductive claim we are trying to prove. For K equals 2, I kind of argued vaguely. That can be the base case. Let's try to worry more about the inductive step. Maybe for intuition, I can start with K equals 3. So again, if I recall the AEL picture, so now I have 3 code words, H1, H2, H3. They are distinct code words. All of this only makes sense when H1 through HK are distinct. First of all, there must be at least some delta out fraction where not all are equal on these local vertices. There might be vertices where H1, H2, H3 are all equal. There's no reason for them not to be. But at least in some constant fraction, they will not be all equal. And each vertex here, based on the local value here, kind of partitions the set 1 through 1, 2, 3 into, yeah, so the partition will look like either 1, 2, 3. So this partition can have size 2, 1, or 3. This is just based on one particular vertex, left vertex. There's a delta out fraction where the partition is of size at least 2.
You're partitioning them based on whether the values are equal or not.
Yes, yes.
So how can it be 1, 2, 3?
All of them can have the same value on one left vertex.
But wasn't this a set of vertices where all of them were not equal?
No, so right now I'm defining it for all L.
Oh,
Yeah. So there's a delta out fraction where the partition is of size at least 2. And in fact, from that, let me take out the most frequent one. That would be some how many partitions there? 3, 4. So at least delta out over 4 vertices, fraction of vertices, will have a common partition of size more than 2. Okay. Let's say it was this particular partition. This is good for us because in this case, all 3 code words are different. 1, 2, 3. So we could try to use the local generalized singleton inequality on all of them. And so this is the easy case. Let me argue why. So let's call the local projections of this H1, H2, H3 as F1L, F2L, F3L. So by the generalized singleton inequality that we have, and even G that we are measuring things against would have some local projection. This is greater than equal to 2 delta because K here is 3. And this happens for a constant fraction. So like term by term, we can say that it's dominated by and likewise for delta G. And this argument is exactly similar to what we had before for the distance proof. Because in this delta out over 4 fraction, they differ in some delta GL, comma F1 positions in U star. So these edges will be the corresponding to the red edges that we had before. So again, a similar expander mixing lemma kind of computation will allow us to lower bound this.
Can you say again the argument?
Yeah. Can I say this better? Is the distance on it?
Shashank, you're showing this by arguing using this, the whatever, the property
Yeah.
right there. right?
For the inner code,
The
yes.
inner code. Okay.
Yes.
Do you need the erasure version here?
For now, no.
For now, no.
Right. So here we had 2 bounds, right? The upper bound was simply expander mixing lemma. And the lower bound was using that for each of these S, which is a delta out fraction, some delta C in times D many edges were being colored. I could also turn this into an average argument. It doesn't have to be a lower bounded degree. If the average delta C in was something, then I would still get the same bound. So making that jump a bit. This U star takes the role of S here. It's of size delta out over 4 now.
U star.
U star is the set with common partition 1, 2, and 3. So these are all vertices where H1 looks different from H2 and H3 looks different.
You're thinking on the left side.
On the left side. So these are vertices where all 3 of them look different. And these I'm calling as F1L, F2L, F3L.
So you're going to be coloring red.
Yeah, so I'm still measuring distance only from a fixed GL, not based on F1L, F2L, and so on. So let's just focus on F1L. I'll be coloring vertices edges based on F1L, where it differs from GL. That on average would be this fraction, expectation over U star, delta GL with F1, F1L. And that average fraction, again, because of that kind of computation, will propagate to everything. So delta GH1 will be approximately this up to lambda. Likewise, delta GH2 and delta GH3. Now, if I sum all of these and use linearity of expectation, for each L, we have the generalized singleton bound. So this is true for all L in U star. And that's why first we singled out U star so that we can use a single generalized singleton bound. And that's it, like the sum of delta GH1, H2, H3 will become 2 delta. So this is actually the easy case. This is saying that if we found a lot of vertices where all 3 of them were different, then whatever is happening locally can be taken global. The more interesting case is if the most frequent partition turns out to be, let's say, 1, 2, 3. So, yeah, this is case 1. This is case 2. Here, now there is only F1L and F. Case 2. The partition looks like 1, 2. So now F12L will be a common thing and F3L is different. So again, we can use the generalized singleton bound, but only for these 2 at a time. And sure, we can also say that delta G H3 is greater than equal to 1. Maybe 3 is still manageable. 1, 2 are less clear. But 1, 2, what we could try to use is these actually count as common error locations for both 1 and 2, for H1 and H2 globally. Because they are, H1 and H2 have a common F12L in these vertices. So they are not just errors, they are common error locations.
You mean now locally with respect to L?
Sorry?
When you said common error locations, it's a local statement?
No, globally. Because on the left side, these H1 and H2 were being equal, right? So wherever those are errors, they are errors for both H1 and H2 globally. So those GL and F12L errors actually lower bound the common error locations. And now finally, we will use the strengthened version to say the first is the strengthened version that I showed with triangle inequality, that for H1 and H2, we lower bound it with delta plus delta G H12, the common error locations. And for these two, the common error locations and H3, we can rely on the local bound again. Slightly confusing. Maybe it's actually cleaner in the.
Maybe,
Sorry.
somehow it is far from me and
Okay.
can
Yeah.
you show it somehow?
Yeah. Maybe the most general case will be actually better.
Shashank,
Yeah.
the question I had is, so this partition or whatever, the local view is maybe only like, so it's
The local view is on
the local thing on the
Yeah.
list, but because you can just make lambda be like,
Yes. Yes.
Smaller.
Exactly. Yeah. That's where the doubly exponential also comes from. Like.
okay, you have you have something double exponential.
Yes.
That's all absorbed in the epsilon.
Sorry.
That's all absorbed in this like minus epsilon.
Yes. Hope it is. So it's not absorbed in the epsilon. I'll show you where the dependence comes. Okay, so let's start with this set H called H1. HK. This is our goal is to show delta G, the common error locations. That's the strengthening that we were going for. Okay. We did the entire partition idea that each L on the left hand side partitions based on the local value that it gets. Let's look at the most frequent partition that is of size at least 2. A lot of vertices might partition just the entire thing as a common thing. We're going to ignore that. Let's look at the most frequent partition, size at least 2. That would be of size at least delta out over the number of partitions. So that's k to the k in general. And let's say this partition is H1, H2, HP, where P is between 2 and k. Okay. So we'll apply induction on H1, H2, HP, all of them individually. With induction, we can always get this. Slightly overloaded notation just means the common error locations there. So this is the inductive step. The delta G HI is the common error locations. I'm going to use that to bound that using the local partition that we are getting. So there might have been originally some common error locations. Those will stay as it is. There's a lot of new ones, which is yes. So because this partition is of size P, we will actually get 3 different local code words for each L, counting up to uniqueness.
So what's this inequality telling us? That this is an inductive logarithm?
No, this one says that, okay, when we started, we had some common error locations with all of K of them. When we reduce the set from H to HI, the number of common error locations might have increased. And this is counting the increase. The increase is essentially coming from what are the new error locations locally that we are seeing. Because all of these HI code words collapsed into one on these L vertices, on these U star vertices. U star was chosen to be creating this partition.
Collapsed into one, they couldn't collapse into parts like.
No, so let me even call this H1. So this is the most frequent partition, which means that for L in U star, all the code words in H1 had a common value on a left vertex. And that common value is F1L. So these values might be different across L, but they will all be same for code words in H1. So the new gain in common error locations will essentially be coming from delta GL and F1L. Okay. Likewise, delta GH2. And so on.
Delta GH is the distance for like the partition where they all would agree or all disagree.
This
Yeah,
term,
that term.
this is the common error locations between G and all of H.
All of them, sorry.
Yes.
All of them. Okay, yeah.
So now if we add all of these up, this term will be, this is a sum of HI minus 1. This is actually going to give me K minus P delta. For the second term, we are going to use this. The first delta GH term is going to be common for everything. That gives P delta GH. For the second term, we can only bound it as a sum. So that's why we need to sum first. This would be the sum.
What's this you just wrote? What is it supposed to?
So I'm just summing these inequalities, starting from here.
Oh.
The first term was giving me K minus P delta. For the second term, I'm using these bunch of inequalities. So I gathered P times delta GH. And this is the remaining term. This sum I can bound using the local inequality, term by term, for every L inside the expectation. So this is going to be, there are P of them now. P minus 1 delta. Except for every L, I will have to erase certain fraction. Because the initial error locations that I had, I'm going to erase everything from those common error locations. So those are SL. So that's the only place where we need this erasure based thing. And then once we push this in, we'll basically get P minus 1 delta.
You then keep erasing it because that was the most common. Then you move to the next one and so on.
That would be one way to do it. You keep growing the set of erasures. But if you just keep track of common error locations, that is also sufficient. Then you don't need to deal with erasures globally. Like here, erasures are only used in this local computation, not globally ever.
But I mean, okay, we dealt with H2. I mean, you had a bunch of different partitions. You took the first one that was most common.
Yeah, so only that is needed. Like other things are handled inductively. So we looked at the most frequent partition.
Yeah.
Here we already use kind of distinctness between code words that are in different partitions, right? And inductively, we would have used distinctness of code words within H1 and so on. But yeah, essentially we look at the most frequent partition, use induction here. And for each of these, we try to gain some common error locations. And that strengthens the induction a bit.
What I don't understand is that you have a huge right-hand side. H1 is only a small part of it. So even if you extracted all of everything you can from that part, what about the rest?
No, so I'm summing all of them, right?
So you are doing a sum for each one, and how are you handling the interaction between them?
So the interaction between them is already kind of being handled here. Right, so essentially at the end of the day, what we want to use is the distinctness of all these code words. So things that are in different partitions, there the local singleton bound is kind of using their distinctness. Because we are applying it for P things at a time.
Okay, I don't understand, but maybe we should take it offline.
Yeah. And just to finish up this computation, I think this is speed delta. Yeah, so this completes the computation. Globally, what we did was we started with these K code words. We let them be partitioned into P parts based on the most frequent partition. And then used induction on each of these sets that we had in the partition. And we combined things together with the partition.
Okay, thanks very much.